Okay, so this is definitely weird, but got to make sense of this stuff. And what we're going to talk about here today is that what's coming in, which is pretty straightforward, what's coming out, where that energy goes. It was a question I asked you guys last week, and just going to try to explain it, get through it. Shouldn't take very long, so bear with me. Welcome to Monday morning. So first things first, I asked this question previously, and it was more or less my idea of asking if the sun's energy keeps on coming and coming and coming and coming and coming, what eventually will happen to Earth? Why doesn't the Earth, for example, melt, catch on fire? Any number of things that happens with heat. And so I posed this question, what do you think would happen, or what do you think happens to this energy? And by and large, you guys were able to answer that question. Really, what happens is a lot of it gets absorbed by the Earth itself, by the oceans, by the atmosphere, and a whole bunch of it is reflected. So it doesn't even actually make it to the surface. So what we really have on Earth is we have this balance, and the balance is affected by these different variables that affect what we call the energy budget. The energy budget for Earth is literally how much energy is coming in and how much energy is going out. So these variables are things like where you are on Earth. So if you live close to the equator, I'm sure you guys are aware that it's warmer. If you live at the poles, it's cooler. So where you are determines how much energy you're receiving on the planet itself. Reflection, this term called albedo, it came up in one of the readings. Albedo is very much how reflective something is. So something white is going to have a high albedo, something that's much darker is going to have a low albedo, and you know that the colors really matter. If something is really, really light in color, it's going to reflect a lot. That surface type really matters. So if it's ice, if it's sand, or clouds, for example, clouds, very bright in color. The clouds do several things. They're reflecting light coming in from the top. If you've ever flown over them in an aircraft, you can see that it's really, really bright up there. And if you're underneath the clouds, of course, the radiation actually that's being emitted by the Earth gets sort of trapped, almost like a blanket. And then you have the atmosphere itself, and the atmosphere will either reflect or absorb, and it depends on the gases, which is another thing I've been trying to point out. So carbon dioxide, for example, in the atmosphere, these trace gases, which are absorbing light as it comes through. Pretty crazy stuff, but you'll see that tomorrow in an online kind of a lab that I hope is worthwhile. We'll see. Either way. And then, of course, you get the planet itself. So Earth is actually absorbing energy. People pointed out like blacktop, walking on blacktop, it's absorbing that light and then it's re-radiating it. You can see it sometimes on the cars or on the street. Then you can certainly feel it, especially like hot sand, blacktop, things like that. So back to this original diagram. Output. How do you have an output energy coming from the Earth? Well, it's actually pretty simple because the sunlight's coming in. The sun's giving off that radiation, the stuff that we've been talking about like the entire time we've had class until we stopped. Yay. So the sun is out there constantly emitting radiation. So the inputs in the Earth system is going to be sunlight. The sunlight's always coming in, always coming in, always coming in. That sunlight is hitting the planet itself, or at least it's trying to. Now, the other thing I need you to understand about incoming sunlight is it's short wave. Remember, as we go from over here in the spectrum this way, the waves get shorter and shorter and shorter and shorter and shorter, and they gain energy as they do that, or they have more energy as they do that. So sunlight in itself is actually short wave radiation. It's very powerful stuff. All that is coming at the Earth all the time. Well, the Earth gets in the way, that light strikes the Earth, and you know that light does those 7 different things. It can do any number of those 7, if not all of them, when it gets to the Earth. So what happens is actually 30% of that light, a third of it, bounces right off. Doesn't even make it to the Earth. So when I posed that question about sunlight hitting the Earth, I didn't actually say that all of it would make it. Some of you actually pointed that out, that not all the light even makes it to the surface. It's about 70% makes it, a third of it bounces right off, doesn't even get through. So what I have here is I have a diagram, I call it follow the energy, but if you look at the bigger version, here's the incoming light. Here's all the stuff from space. So here's 100% right here, and all of that light is trying to get into the Earth, and this is whatever actually makes it through. This comes in, a bunch of it bounces off, a big chunk of it bounces off the clouds. Right away, blam, off it goes. About the same amount gets absorbed by the gases in the atmosphere, and then a whole bunch of it gets absorbed just by the surface. The evidence for that is if you're walking on any surface on the earth on a sunny day, which it's not today because it hasn't been, which is it drives me bananas that I have to be home. I can't be hanging out with you guys, and I'm stuck inside because it's raining all the time. Anyways, lots of light's coming in, a bunch of it bounces off. So let's say based on this, let's say it's like 15% of it just bounces right off without even making it in. So you've got 30% bouncing off anyway, and then you've got more of it bouncing off the clouds, a whole lot of it getting absorbed, and then the rest of it getting absorbed by the surface, and then a whole bunch of it, actually quite a bit, bounces off the surface. So things like snow, ice, all of those white surfaces are going to reflect whatever light hits them, and it bounces right back off. So that gets back off. So really, a lot of that incoming radiation, if it's absorbed, is absorbed by the ground itself and a little bit into the atmosphere. Now, take the sunlight away. The Earth is actually what we call re-radiating at all times. So that surface re-radiation is actually constantly trying to escape, so to speak. So let's say it's nighttime over here, no sun. The Earth is always giving off some of that warmth, and a lot of it is getting trapped here in what they call the atmospheric window. It's not getting out of the air, it's stuck there. Some of it actually makes it all the way back out into space. Not very much, a tiny percentage of it, but a lot of it is going into the atmosphere, and then those gases trap it, and it kind of comes back and it sort of circulates right around that layer that we live in called the troposphere. It's a really thin layer. It's not actually very deep, but it's helpful because there's oxygen, and if there weren't these things, we wouldn't be alive anyway. And then, believe it or not, clouds are actually constantly re-emitting heat. The weird thing about clouds is, if you go up into the atmosphere and jump out of an airplane, for example, it's usually pretty cold up there, but if you fall through a cloud, they're very warm. So they're constantly giving off that warmth, but we just don't think of clouds as very warm creatures, but they really are. So clouds are constantly giving off heat. Some of it is still escaping, but it's a balance. Notice it's about a 50-50 balance, which keeps the temperatures on Earth really stable, regardless of where you are. So, back to radiation. Anytime anything absorbs light, anytime, and we've seen this in the lab, the temperature will change. In fact, it'll go up. Anytime you're shining light on any surface, the temperature has to go up. And all objects actually give off light. I give off light. You guys give off light. Anything that has a temperature gives off light. And the neat thing about that is the amount of light that it gives off and the wavelength of that light is actually totally dependent on the temperature of the object. So the warmer the object, the narrower that wavelength. And I'll show you an example of that in just a second. Now, as that temperature goes up, higher temperature, higher energy, that wavelength gets shorter and shorter and shorter. And the cool thing about living in the 21st century is you can actually see that. So main points, anything absorbing energy warms up. All objects are going to give off energy or radiation because of that temperature. And as that temperature goes up, the wavelength shrinks. It gets smaller and smaller. And we can see that using infrared technology, which is really cool. If you look at this picture, you can probably figure out what this animal is just by looking at it. And all you're seeing is a temperature heat signature of light that's being given off by this animal. I give off light, you guys give off light. You can see where it's warmer because the wavelength has changed. You can see where it's colder because the wavelength has changed. So really what you see is as you progress in temperature, you can see different wavelengths. And that's what scientists use very often to look at how the temperatures change on Earth. You can see all of this from space just looking at infrared wavelengths. And infrared is important, but I'll get to that later. Okay, infrared is the very important one, mainly because it's related to temperature, but we'll get to that later. So, we know the Earth absorbs and re-radiates energy. We can feel it. I've tried to show you in diagrams. It's absorbing energy during the day, it's re-radiating that at night, even during the day it's doing it. That's why we can feel heat off a blacktop. And when you consider the energy budget of the whole planet, everywhere is considered, everywhere. The atmosphere is considered. So the energy that's in there, the energy that's bouncing off of it. The land, what I was talking about before, the land is absorbing energy. The ice, which doesn't absorb very much, it reflects a lot, which is very important. The ocean, which is constantly absorbing energy, constantly. So think about this piece. If the ice is not sitting on top of the ocean, reflecting it, the ice melts and is gone, the oceans now can absorb even more, which can be more of a problem because it messes with the budget. And then even the life. So you and I, all of the trees, all of the life, all of the grass, all of the plants, everything, all of the biosphere is still absorbing and releasing and using energy, which some of you actually pointed out, because humans are actually using some of that energy. So when we talk about the most important parts of the energy, we're talking about heat. And heat comes in a variety of wavelengths, like infrared. So you have infrared light that's not really strong, so it's kind of warm to the touch. You might be able to feel it. Even cold things count as infrared. And then you've got really powerful infrared, the stuff that burns us when we touch it, really high wavelength. The neat thing about that wavelength is if you chart that wavelength in intensity and amount, it actually matches exactly with what's coming in from the sun. The difference is that when it comes from the sun, it's more powerful. It's a higher wavelength. It's down here, or shorter wavelength, higher energy. So when that hits the earth absorbs it, re-radiates it. If you look at that and chart it, the neat thing about that is even though it's a different wavelength, it's much longer, so it's infrared, it's the same amount. So if you look at the area under this curve and this curve, they're the same. So it's the same amount. The earth is very well balanced in terms of how much energy is coming in and how much energy is leaving, which is pretty neat to think of. You mess with those and, well, you mess with the balance, which is what we're worried about. So to sum up, sort of, we've got light coming in from the sun, short wave, very powerful, short wave radiation, way down here on the spectrum. And then you've got the earth constantly re-radiating that, but it's longer wave. It's not as powerful. It's infrared. It's stuff we can feel as humans. The whole diagram is one, back to it. Sunlight's coming in as short wave, really high energy. The earth gets in the way of that light. 30% of it bounces right off. Doesn't even get through the atmosphere, just 30%. 70% makes it. The earth absorbs that 70%, so it's not absorbing all of it, it's absorbing a lot of it, but not all of it. And then it re-radiates that same energy either back into space or into the atmosphere or into the earth itself. And that's long wave. So it takes it from short wave, powerful, to long wave, not nearly as powerful radiation, okay? That's the way the budget works. Now, the last piece of this puzzle is in something called PhET. And PhET is an online simulation that I'm going to ask you guys to do probably starting tomorrow. And you'll get to see how these different molecules actually trap the infrared radiation. So there's only a very small part, those trace gases that I mentioned, those trace gases absorb that extra radiation that otherwise would escape into space. And we call them greenhouse gases because they act like a greenhouse. They warm everything up, which is actually good. If you take that away, we die because it gets too cold. Now, those gases are pretty common gases. Water vapor is a greenhouse gas. Carbon dioxide is a greenhouse gas. And the next lesson will actually show you why they're important in our atmosphere. You take those away, we lose this. But when you start messing with how much there is, it messes with the balance. Okay, I hope that was as fun for you as it was uncomfortable for me. Hope you guys are doing well. Please continue to message me best you can. And yeah, good luck.